you're not going to use this, you're just going to use the rule, the x to the n rule, right? But you could have used this. Okay? So this is the original definition of the derivative. Now, going back to this picture, we have this function which we really have no rules for. We don't have any rules. All the rules that we have don't work. The x to the n rule is not applicable. This is not x to the n. I made some discussion of this a long time ago, I think, where I said this is so much different than this. So these are not the same function. So I can't use the rule that I have here. Not the same function, so you can't use it. So what are we going to do? Well, if we don't have any rules, then what could we revert to? We could revert to the definition. Well, we could try and use the definition. Now, it turns out that it's not going to be nearly as simple as this to use the definition. And the manipulations that you have to do are not going to be as short as this was. Okay, but you can look it up, and it's not that hard to see. But there's some tricky stuff in there. So it's a little subtle, and for the length of our class, we don't really have the time to do it. But you can certainly look it up, and it's definitely not impossible to follow. In fact, it's even in our book, and it's not impossible to follow at all, but I'm not going to do it. I'll just tell you the answer. Okay, so I'd like to know, if this is f, I'd like to know what is the derivative of that. Okay, and as I said, you can look it up in the book, you can look it up on the internet. It's not impossible to read it, and I think you could do it without much difficulty. Okay, but I'll just tell you the answer. But the answer is kind of surprising. Okay, the answer is surprising. There's only one function that has this kind of situation, and that's this function. So, I mean, like, for example, if the original function was not that function, but was x squared, the derivative is definitely not x squared, right? The derivative is what? Is 2x, right? It's not equal to x squared, right? Right? And if the original function was x cubed, the derivative is definitely not x cubed, right? In fact, it's what? 3x squared. Okay, so generally, the function and its derivative are never the same. There's only one function where the function and its derivative are the same. Which it sounds weird, but and that's this function. E to the x, the derivative of e to the x is actually e to the x. What does that mean? It means that if I want to know the slope, suppose I want to know the slope right here. Well, okay, I'd like to know the slope right there. So I need the derivative. So the derivative of this, I'm telling you, without proving it, is also e to the x. So what is the slope right here? Well, how do you know? You put 0 into the derivative. The derivative is this. If I put 0 into that, I get what? 1. So what's the slope right here? 1. What's the slope when x equals 1? So that means I want to know what's the slope right there. So how do I know the slope right there? I put the 1 into the derivative. So if I put the 1 into the derivative, what do I get? E to the 1, or e. So what's the slope? E, which is what? Between 2 and 3. The slope is between 2 and 3. But that's kind of weird because the slope is the same as the height of the function. Right? So the height of the function here is what? 1, and the slope is 1. The height of the function here is e, and the slope is e. Anyway, just weird, but that's the answer. Okay? So this is the only function whose derivative is the same as the function itself. I guess that makes it really simple to do the derivative. Right? I guess it's just the same thing. You don't even have to do anything. But anyway, that's the only function that has that property. Okay? So what is the derivative of e to the x? E to the x. Okay, so you have one more function that you know how to do derivatives of. Right? So you can do, what functions can we do? We can do powers, all powers. We can do polynomials. And now you can also do e to the x. And you can also do square roots, right? If f of x is equal to the square root of x, you can do that too, because that is equal to x to the 1/2, and you know how to do that. Right? And you can also do functions like this. Right? Because that's x to the -2, and you know how to do that. Okay? But now we added one more that you know how to do, and that's e to the x. Now, let me just stretch your memory a little bit and ask you to do this. Now that we know that new fact, now that we know that the derivative, if f is e to the x, that f prime implies, this means implies, that f prime is also e to the x. Right, we know that. Okay, now that we know that, let me stretch your mind a little bit and say, suppose f of x, or let's use a different letter. Suppose g of x is equal to e to the x cubed plus x squared. Like that. Now, you actually know how to do this. That is, you actually know how to do this. But I'm not sure you can do it. But you have the tools to do it. But not so straightforward. So, what rule are we going to have to use here? So, not so, I'm not sure you'll know, but you could know. Okay, so let me just give you the clue. And that is, let me ask you, can you write g of x, this function, as like a composition of, like, for example, call it h of k of x. Can you express g as the composition of two functions? Remember, I tried to impress on you, remember I said when you're a young kid, you had to learn that 5 plus 3 equals 8, right? And then I said, like a year later, your teacher reversed the question and said, can you break up 8 into two smaller numbers? Right? And then you had to go back and twist your brain around a little bit and come up with 5 and 3. Right? And I'm asking you to do something like that here. In other words, starting with something more complicated, can you break it up into two smaller pieces? Now here I'm asking you to break it up into two pieces where you're adding those two pieces. But here I'm starting with this function and asking you to break it up into two simpler functions that you make their composition to get this function. So I want to know the h and the k, just like I want to know the 5 and the 3. So what could the h be? And what could the k be that would do this? So in other words, we talked about the outside function and the inside function. So in this notation, which is the outside function and what's the inside function? The outside function is what? Is the h, and the inside function is the k, right? So I want to try and see this as the composition of an outside function and an inside function. So if we're going to do that, what would the outside function be? What? Yeah, who said that? Oh, okay. E to the x, right. That's right. So the outside function is e to the x, and the inside function is what? Let's make sure, is this right or not? Do h of k of x. Here's h. Right? Here's h, and here's k. So what I'm saying is put k into h. So if I put x into h, I get e to the x. So if I put k into h, I get e to the k of x. Right? So if I do h of k of x, I don't get e to the x, I get e to the k of x, right? But what is k of x? This. So what do I get? E to the x cubed plus x squared. That's what I wanted to get. Right? Okay? So, here's the function I started with. And I want to know the derivative of this, but I stopped it with the derivative question for a minute. And I just said, can you break this down into composition of two simpler functions? That is, can you write this g as the composition of an h and a k? Right? Can you write it as the composition of an h and a k? And we did it. Here's the h, and here's the k. Now, why did I do that? Why did I stop going from here when I'm trying to find the derivative of this and stop that and say, can you write this as the composition of these two? Why did I shift to that question? Because if you can write g as the composition of two functions, then what rule can you use? What's the name of that rule? The chain rule. The derivative of this, that is the derivative of this, there's a chain rule for that. If you remember, if you want to know the derivative, I'm using this notation now, the derivative of h of k of x, what is the chain rule for that? What is the chain rule for that? It's h prime, well, it was two parts. It was one part times another part. And the right-hand side was the easiest part, which was just k prime. And the other side was h prime, but not just h prime of k of x. Okay, so maybe that's kind of straining your memory, since you have so many kanji that you've stuffed into your memory. So you don't have space for this. But that is what we said. So the derivative of a composition can be gotten with this rule. This is called the chain rule. Now, I wanted to know the derivative of this, but this is not the composition. At least it doesn't originally appear as a composition, but I stopped and said, can I think of this as the composition of two simpler functions? And we got the answer. It was these two simpler functions. So now we can use the chain rule for the derivative of this. That is the derivative of this. And the chain rule says it's going to be these two. So for our k and our h, what do we put in here? So k is here. So what's the derivative of this? That's easy. What's the derivative of k? That's the easy one. Just what? 3x squared plus 2x, right? Okay? The derivative of this is easy. And that's what I need for this part, k prime, so I have to put that here. So what is that? 3x squared plus 2x. Okay, that's that part. That was pretty simple. But this part, it looks a little bit worse. So what does this part mean? It means I have to find the derivative of h, and then don't just put in x though, put in k into that derivative. Right? That's what it means. Because it doesn't say h prime of x, it says h prime of k. So instead of putting in x, I have to put in k after I find the derivative of h. Okay, so what is h? Here's h. So what is h? E to the x. So what is the derivative of that? E to the x, right? That's just an easy one. But I don't want to put in x, right? I don't want to put in x, I want to put in what? K. So it's, I'll make it in 2 steps, all right? E to the, not e to the x, but e to the k of x. Right? That's what it says. So finally, if I write this again, I get that times that. This part is 3x squared plus 2x. And this part is e to the k, which means e to the what? So that's pretty weird, but it's true. Is that right? Yes, it's right. Okay, so that's the answer. So I said, we started out asking about this function e to the x, and we said, what's the derivative of e to the x? This function here, what's the derivative of that? We don't know how to do it, but I gave you the answer. It's e to the x. Then I said, okay, now, how about if I asked you this question? That looks really hard. It is hard, actually. It's a little hard. Okay? But how can we do it? If we can see this as the composition of 2 simpler functions, then we're allowed to use a rule, the chain rule. So I asked you, can you see this as the composition of 2 simpler functions? And somebody said, yeah, the outside function would be e to the x. And the inside function will be this. So now I've written this as the composition of these 2. Now that allows me to use the chain rule. The chain rule will give me the derivative of a composition like this. The derivative of a composition is given by this chain rule here. So now I have to figure out what this is and what this is. I did this one first. This one was easier, so I did this one first. And then I had to do the derivative of this one, and I got that. And finally, I get that answer. Okay? So, that's it. The first time we really needed the chain rule. Well, no, that's not true. No, that's not true. Because yeah, in a sense, that's the first time we really needed the chain rule. We sort of definitely need the chain rule. If I ask you like this, if I give you that function and ask you to find the derivative of that, you really need the chain rule, because you never would want to first multiply this out 100 times and make this into a polynomial. You could do it that way. You could multiply this out 100 times, get a polynomial, and then you don't need the chain rule. Just use the polynomial, derivative of a polynomial. That's easy. But of course, you never want to multiply this out 100 times. So you really need the chain rule here too, but not absolutely need it. But in this one, You absolutely need the chain rule, otherwise you can't